When people talk about time, they usually sound very confident. They say things like time flows, or time passes, or time goes forward whether you like it or not. Everyone nods because it feels right. We all wake up in the morning. We remember yesterday and we worry about tomorrow. It feels so natural that it almost seems silly to question it. But physics has a bad habit of questioning things that feel obvious. In fact, the more obvious something feels, the more suspicious a physicist becomes. So, let me start with a simple confession. We do not really understand time. We use it. We measure it. We depend on it. But understanding it is another matter. And the reason is not poetry or philosophy. The reason is that when we look closely at how nature works, time refuses to behave the way our intuition says it should. In everyday life, time feels like a straight line. Events happen in order. Causes come before effects. You throw a glass, it breaks. You never see the broken pieces jump back into your hand and reassemble themselves into a perfect glass. This gives us a strong feeling that time has a direction like an arrow pointing from past to future. This feeling is so powerful that we quietly assume the laws of nature must care about that direction too. Now, here is the first surprise. Almost all the basic laws of physics do not care which way time points. If you take the equations that describe motion, forces, electricity, magnetism, even the behavior of atoms, and you replace forward in time with backward in time, the equations still work just fine. Nature, at least at the level of its rules, does not seem to mind running the movie backward. This is already strange. If the laws do not care about direction, why do we remember the past but not the future? Why does heat spread out and never gather itself up again? These questions bothered scientists for a long time, and they still do. To make progress, physicists did what they usually do when confused. They tried to build simple models that work, even if they do not answer every deep question right away. In classical physics, time is treated like a quiet background. It is just there ticking along at the same rate everywhere, like a giant cosmic clock. Isaac Newton imagined time as something absolute, the same for everyone, whether you are standing still or moving fast, whether you are near a star or floating in empty space. This idea worked extremely well. For centuring it, we learned how planets move, how bridges stand, how waves travel, and how machines work. Calculus fit beautifully into this picture. Calculus is often feared, but at heart it is very simple. It is a way of talking about change. A derivative tells you how fast something changes at a given moment. An integral tells you what you get when you add up many tiny changes over time. When time behaves nicely, calculus behaves nicely too. You slice time into small pieces, study what happens in each slice, and then add everything together. For a while, it looked like physics had the universe figured out. Then reality pushed back. At the beginning of the 20th century, experiments started giving answers that did not fit this comfort picture. Light behaved sometimes like a wave and sometimes like a particle. Atoms emitted energy in sudden jumps instead of smooth flow. And when people looked closely at very fast motion or very strong gravity, time itself started to misbehave. Relativity showed that time is not absolute. Two observers moving differently can display how much time has passed between the same events, and both can be right. Time can stretch and shrink. It can mix with space. The idea of a single universal now dissolves. That alone is enough to make your head spin. But quantum physics went further. It did not just bend time. It questioned the idea that events even have definite history. At the scale of atoms and particles, nature does not behave like a tiny version of everyday objects. You cannot say that a particle definitely went from point A to point B along one clear path the way a thrown ball does. Instead, experiments show something very strange. Particles act as if they explore many possible paths at once. This is not a metaphor. It is not ignorance. It is how nature behaves. If you fire electrons one at a time toward a screen with two small openings, each electron lands at a single spot. But after many electrons, a pattern appears that can only be explained if each electron somehow went through both openings, interfered with itself, and chose its landing place according to a rule that involves waves, not straight line. At this point, you might think the problem is that we do not know enough. Maybe the electron secretly picks one path, and we just do not see it. But decades of careful experiments show that this idea does not work. Nature really does seem to consider multiple possibilities at once. Now comes the uncomfortable question. If particles explore many paths, what about time? Do they explore many histories as well? This question turns out to be unavoidable. And once you ask it, time starts causing serious trouble. In classical thinking, a particle has one. In quantum physics, a particle does not even have a single position until you measure it. So what does it mean to say what it did before you looked? Did it take one route? Did it take all of? And if time itself is flexible, can some of those routes involve time behaving in ways we do not normally allow? Physicists tried many ways to avoid these questions. They invented clever rules for calculating probabilities without talking too much about what really happened. These rules worked, but they were clumsy. They felt like instructions rather than understanding. You could follow them and get the right answer, but you did not feel you were seeing the machinery of nature clearly. There was a growing sense that something simpler was hiding underneath. To see it, you have to let go of a deeply rooted habit. The idea that nature chooses a single path and then follows it. Instead, imagine that nature is much less decisive. Imagine that it considers every possible path a particle could take between 2 points. Straight paths, curved paths, crazy zigzag paths, even paths that go backward before going forward again. At first, this sounds insane, but stay with it. Suppose you want to know how a particle moves from one place to another. Instead of asking which path does it take, you ask what is the contribution of every possible path. Each path contributes something like a tiny arrow pointing in a certain direction with a certain length. When you add up all these arrows, most of them cancel out. They point every which way. But a small set of paths line up and reinforce each other. The result of that sum is what you observe. This way of thinking changes everything. The particle does not choose a path in advance. The path you observe is the result of interference among possibility. Here is where calculus quietly returns in a new role. Instead of integrating over time in a single history, You integrate over histories themselves. You add contributions from an infinite number of possible motion. This sounds impossible, but mathematics has a way of making sense of infinities when they are handled carefully. What matters is not each path by itself, but how paths compare to each other. Tiny changes in a path can make large changes in how its contribution point. For most paths, neighboring paths point in opposite directions and cancel out. Only near certain special paths do the contributions stay aligned. Those special paths are the ones that look classical. They are the paths of least action, the ones Newton would have recognized. So classical motion is not wrong. It is what survives when many possibilities cancel out. Now we reach the heart of the discomfort. Some of the paths that must be considered do not respect our usual sense of time. They may involve loops, detours, or segments where time runs backward. Not backward in the sense of movies reversing, but backward as a parameter in the mathematics. At first, this seems like a cheat. Why allow such strange things? The answer is simple. If you forbid them, the calculations stop working. Nature's bookkeeping insists that they be included. This does not mean that we see people growing younger or cups unbreaking themselves. Those backward time paths do not show up directly in experience. They cancel out in ways that leave the macroscopic world behaving normally. But at the microscopic level, they are part of the accounting that makes the predictions come out right. This idea is deeply unsettling because it attacks a belief we did not even realize we were carrying. That time itself enforces morality. We think the universe knows the difference between past and future. But the equations suggest something colder and more neutral. They suggest that consistency matters. To understand why this works, think about waves on water. You throw two stones into a pond. The ripples spread, overlap, and interfere. At some points, they add up. At others, they cancel. You do not say that the water chooses which ripple is real. All of them are real, and the pattern you see is the result of their combination. Quantum physics works the same way, except the waves are not in space. They are waves of possibility. Time in this picture is not a one-way street. It is a coordinate used to label events, and the rules that govern those events are remarkably tolerant about how that coordinate is used as long as everything fits together consistently. This perspective helps explain another mystery that troubled physicists: antiparticle. In experiments, particles appear that look just like familiar ones, but with opposite electric charge. Instead of inventing a completely new kind of object, the mathematics suggests something astonishingly economical. These antiparticles can be treated as ordinary particles moving backward in time in the equations. Again, this does not mean they literally travel into the past in any dramatic way. It means that when you account for all possible paths, including those with reverse time direction, the behavior of matter and antimatter falls neatly into place. What matters here is not the imagery, but the bookkeeping. The universe seems to prefer methods that are simple and symmetric, even if they offend our intuition. At this point, you might feel uneasy, and that is a good sign. Physics does not exist to make us comfortable. It exists to describe how nature behaves. If nature turns out to be strange, our comfort is not part of the calculation. The real test of an idea in physics is not whether it sounds reasonable, but whether it works. Does it predict experiments correctly? Does it make new predictions that come true? Does it simplify what was previously complicated? This way of handling time and possibility does all three. It turns horribly messy calculations into manageable ones. It predicts experimental results with astonishing accuracy, sometimes agreeing with measurements to more decimal places than any other theory in science. And it reveals an unexpected unity between motion, time, and probability. But it leaves us with a philosophical itch we cannot quite scratch. If time is so flexible at the fundamental level, why does our everyday world feel so rigid? Why does the past feel fixed and the future open? The short answer is that large systems wash out delicate effect. When many particles interact, the cancellations that protect ordinary causality become overwhelming. The strange paths still exist in the accounting, but their effects vanish into noise. What remains is a clean, forwarding story that our brains are very good at telling. So the arrow of time may not be a law written into the universe at the deepest level. It may be an emergent habit, a statistical effect, a story that becomes inevitable when you deal with many interacting parts. This is not the end of the mystery. It is the beginning of a better way to ask questions. Instead of demanding that nature match our intuition, we can ask what rules allow the universe to be both deeply strange and reliably predictable. When we do that, time stops looking like a dictator and starts looking like a tool. And once you see time that way, you are ready to follow the idea to its full power. Where paradox turns into precision and where allowing the impossible becomes the most practical thing you can do. If you accept, at least for the sake of argument, that nature keeps track of all possible paths, including very strange ones, then a new question appears immediately. How does nature decide how much each path matters? If everything is allowed, why does anything in particular happen at all? The answer is subtle, but it is also beautiful. Each possible path contributes a little piece to the final result. And that piece has both a size and a direction. Like an arrow, the size tells you how important the path is. The direction tells you how it combines with all the other paths. When you add up all these arrows, most of them cancel out. Only a small number survive in a noticeable way. What determines the direction of each arrow is something called the action. The action is not mysterious. It is just a number you can calculate for any path by adding up how the system behaves at each moment along that path. You can think of it as a kind of cost assigned to a path. Paths with wildly different actions tend to cancel each other because their arrows point in very different directions. Paths with nearly the same action reinforce each other because their arrows line up. This is where advanced calculus quietly does the heavy lifting without needing to show its muscles. Instead of solving one clean equation of motion, you are effectively summing over infinitely many possibilities, but you are not doing it blindly. The structure of the mathematics ensures that only certain patterns survive. What looks impossible at first becomes inevitable once you see how cancellation works. This explains something that puzzled physicists for a long time. Why does classical physics work so well when quantum physics is supposedly more fundamental? The answer is that classical motion is what you get when many nearby paths agree with each other. In that case, small variations do not change the action much. So the arrows point almost the same way. They add up instead of canceling. The familiar laws of motion emerge naturally, not because they are imposed, but because they are stable under interference. So classical physics is not wrong. It is incomplete. It is a summary of what happens when you stop caring about fine detail. Now let us return to time, because this is where things become truly unsettling and at the same time incredibly useful. In this framework, time is treated just like space. It is a coordinate along which paths are drawn. When you allow all possible paths, you cannot logically forbid paths that wander backward in time any more than you can forbid paths that wander sideways before going forward. If you try to forbid them, you break the symmetry of the mathematics and the predictions stop matching experiment. This does not mean that nature has a preference for backward time travel. It means that when nature does its accounting, it does not label certain paths as immoral or illegal. It includes them and lets interference do the policing. Here is the crucial point that prevents chaos. Backward time paths almost always cancel out. They are like scribbles that overlap so densely that nothing readable remains. Only in very specific situations do they combine in a way that produces a measurable effect, and when they do, that effect looks perfectly ordinary from the outside. One of the most striking examples is the behavior of particles and antiparticle. Instead of inventing a separate rule book for antimatter, the mathematics allows you to treat an antiparticle as a particle following a path that runs backward in time between two events. This is not a statement about what we see with our eye. It is a statement about how contributions are counted in the calculation. From this point of view, creation and annihilation events are not dramatic exceptions. They are just places where paths bend in unusual ways. The same underlying rules apply everywhere. What makes this approach powerful is not that it answers philosophical questions about time, but that it makes calculations simpler and clearer. Problems that once took pages of careful bookkeeping can be drawn as pictures and understood at a glance. Interactions become intersection. Complicated algebra becomes geometry. This is not an accident. Nature seems to favor descriptions that are economical. When you find a way to say more with less, you are often closer to how the universe itself operates. Of course, there is a price. The price is that you must give up the demand that nature match your storytelling instincts. You must stop insisting that events follow a single clean narrative from beginning to end. Instead, you must accept that what we call what happened is a summary of a much richer underlying process. At this stage, many people ask a reasonable question. If all these strange paths exist, why do we never notice them directly? Why does everyday life feel so orderly? The answer lies in numbers. The world around us is made of an enormous number of particles when many particles interact. The delicate interference patterns that matter at the quantum level get washed out. The cancellations become overwhelming. What survives is the most stable pattern. And that pattern looks classical. It looks like causes proceed. It looks like time flows in one direction. This is not because time suddenly changes its rules. It is because the bookkeeping becomes brutally efficient. Any path that would noticeably violate everyday causality is canned by countless neighboring paths. The universe does not forbid strange behavior. It simply makes it irrelevant at large scales. This idea has a humbling implication. The arrow of time, which feels so fundamental to us, may not be fundamental at all. It may be an emergent feature like the smoothness of water seen from afar. Up close, water is chaotic, full of motion in all directions. From a distance, it flows calmly downhill. Entropy, the tendency of disorder to increase, fits naturally into this picture. It is not a commandment carved into the laws of physics. It is a statistical fact about large systems. There are far more disordered states than ordered ones. So, paths that move toward disorder dominate the accounting. Time appears to have a direction because disorder is easier to reach than order not because the laws demand it. This perspective does not make time less. It makes it more interesting. Time becomes something that arises from the collective behavior of matter rather than something imposed from outside. One of the most satisfying aspects of this way of thinking is its honesty. It does not pretend that the universe is simple in the way we wish it were. It admits complexity at the foundation, but shows that simplicity emerges naturally when you stop asking for microscopic perfection. This also explains why physics can be so successful even when our understanding feels incomplete. You do not need to know which path a particle really took. You only need to know how all possible paths. Come on, nature gives you the answer whether or not you feel comfortable with the process. This attitude runs through much of modern physics. We calculate what we can observe. We build models that reproduce those observations with clarity and economy. When deeper questions remain, we keep them in mind, but we do not let them stop us from making progress. There is a lesson here that goes beyond physics. The universe does not explain itself in the language of human intuition. It explains itself in patterns, symmetries, and cancellations. Our job is not to force those patterns into familiar stories, but to learn how to read them. If you feel that this view of time removes something meaningful, consider the alternative. A universe that strictly enforces a single timeline with no room for flexibility would be fragile. It would break easily under small changes. The universe we observe is robust. It allows enormous freedom at small scales and produces reliable behavior at large scales. That is not a flaw, it is a feature. When you look at it this way, the strange treatment of time is not a trick. It is a necessity. It is how nature achieves both creativity and consistency at once. So where does this leave us? It leaves us with a picture in which time is not a master, but a participant. It takes part in the rules of interaction, but it does not dictate outcomes by itself. Outcomes arise from the sum of possibilities filtered by interference and reinforced by stability. This picture has been tested relentlessly. It survives every careful experiment we can perform. Its predictions match reality with astonishing precision. When theory and measurement disagree, it is almost always because we have made a mistake in the calculation, not because the framework itself has failed, that does not mean the story is finished. There are still deep questions about time, especially when gravity enters the picture in extreme way. But the lesson so far is clear. Progress often comes not from solving a paradox, but from learning how to live with it productively. By allowing time to misbehave in our calculations, we gain the power to describe nature with unmatched accuracy. By giving up the demand for a single clean narrative, we uncover a deeper order that does not depend on our preferences. If there is one thing worth carrying away from this, it is this: when nature refuses to fit your intuition, do not argue with nature. Change your intuition. Learn to think in terms of possibilities rather than certainties, patterns rather than stories, and consistency rather than comfort. Time will still tick on your clock. You will still remember yesterday and plan for tomorrow. Nothing about daily life is threatened by these ideas. But underneath that familiar surface lies a universe that is far more flexible, far more subtle, and far more interesting than common sense would ever suggest. And that, for a physicist, is not a disappointment. It is an invitation.